Good morning. So far, we have seen about butterworth filter approximation. So today we are going to see about how to determine the order of filter using Ceviche. Okay. So given specification to be the passband attenuation is 3 decibel, stop band attenuation is 16 decibel, passband frequency is 1 kilohertz, and stop band frequency is given as an 2 kilohertz. So we are going to determine the order of the filter. Okay. So we know the specification that alpha p, alpha is, whereas here passband frequency it is given. So we know that omega and the relation between omega and frequency to be 2 pi s. So we'll be calculating 2 pi 1000, 1 kilohertz equal to 1000 hertz. So it will be 2000 pi. And apart from the 2 kilohertz, we'll be having of an 4000 pi radian per second. Okay. So this is the step 1 to be the given data. Step 2, we are in need to find the order of the filter. So how will be finding the order of the filter? So n should be greater than or equivalent to cos h inverse square root of 10 to the power of 0.1 alpha s minus 1 divided by 10 to the power of 0.1 alpha p minus 1 divided by cos h inverse of omega s divided by omega p. Okay. So in the case of Butterworth, what we have seen about an log to the base 10. Okay. So substitute the value of alpha s and alpha p, omega s and omega p, and by substituting all the values, we'll be getting the value of n should be greater than or equivalent to 1.91. Okay. So then after that, what you have to do, we have to round the next highest integer value. We have to round the next highest integer value. So the value of n is equivalent to 2. Next step, we have to find out the value of minor axis and major axis. Okay, so it will be denoted by means of an A and B. So before that, we are in need to know the value of an epsilon and mu. Epsilon and mu over there. Okay, so what is the value of epsilon? Epsilon is equivalent to square root of 10 to the power of 0.1 alpha p minus 1. So which is equivalent to, so substitute the value over that, and we'll be finding the value of epsilon is equivalent to 1. And the relation of mu is equivalent to epsilon inverse plus root of 1 plus epsilon to the power of minus 2. So substitute over that, and we'll be getting the value of mu is equivalent to 2.414. Okay, and the major and minor axis for A and B has given the formula omega p into mu to the power of 1 by capital N, where n is the order of the filter, minus mu to the power of minus 1 by n divided by 2. We know that omega p is equivalent to a passband frequency, which is nothing but an 2000 pi, and omega is equivalent to 2.414. So whole to the power of n value to be 2, and then we'll be obtaining that A is equivalent to 910 pi, and the value of B is equivalent to 2197 Okay, the next thing, so we have to find out the poles over that, and the formula S is equivalent to A cos phi k plus JB sin phi k, where k is equivalent to 1, 2. Okay, so whereas in the case of an pi, which is equivalent to pi by 2 plus 2k minus 1 divided by n into pi over there. So when we are finding the poles over here, we will be finding the value of pi is equivalent to pi by 2 plus 2k minus 1 into pi divided by 2n, where the value of k will be varying from 1, 2. So by if k is equivalent to 1, substitute over here. So it will be equivalent to pi by 2 plus 2 minus 1 divided by, where n is equivalent to 2. So pi by 2 plus pi by 4 will be equivalent to 135. And similarly for k is equivalent to 2, we will be getting of an, so 4 minus 1, 3 pi by 4. So the angle will be getting 225. So how are you finding the poles S1 now? So A cos, that is to be the pi k, for k is equivalent to 1, upper 910 pi cos 135 plus j 2197 pi into sin 135. So when you are substituting over here, the equation will be getting minus 643.465 plus j 1553. Similarly, substitute the value for k is equivalent to 2 and 5k value. Okay, so we'll be getting the value of h2 over here. So when you are finding the denominator of h of z, so this is the expression of an same value. So s plus 643.465 plus 1 5 by 4 the whole square. Okay, So when you are substituting S is equivalent to 0, so what will happen? H of S is equivalent to, so this divided by your root of 1 plus epsilon squared, and we know the value of epsilon is equivalent to 1. By that we can able to find the value of an transfer function H of Z. So this is the way to design our Chebyshev filter. Okay. So far we have seen about how to design a Butterworth filter and the Chebyshev filter. Okay. The next we have to see about how to design the IAR filter from an analog filter. So we'll have often 4 different methods. One to be the approximation of derivative, second one to be the impulse invariance method, third one to be the bilinear transformation, and the fourth one to be the matched Z transform technique. So when you are doing for an approximation derivative, so analog to digital domain, we have to replace S is equivalent to 1 minus Z inverse divided by T. That is, we'll be giving the expression H of Z. That is, we have to find out the value of H of Z. So the H of S will be given over on it. So S has to be replaced by 1 minus Z power minus 1 divided by T. So let me do the problem. Convert the analog bandpass filter with system IAR. He of S is equivalent to 1 by S plus 0.1 the whole squared plus 9 into digital IAR filter by using any one of the derivatives. Okay. So we have to do it out. We have to do by S has to be replaced by 1 minus Z power minus 1 divided by T the whole squared. So 1 minus Z power minus 1 divided by T plus 0.1 the whole squared plus 9. So you take a cross multiplication. So actually it is the form of an a plus b the whole squared. So a squared plus b squared minus 2ab. Then after that do the cross multiplication among the factor and then multiply with the value of plus 9. Then again bring out all the factors into an numerator and then substitute the value of t is equivalent to 0.1 second, so that we'll be getting the final expression value equivalent to 0.91 plus or minus j.2. So when you are doing of an approximation of derivatives, you have to keep it in your mind that Z has to be, S has to be replaced by 1 minus Z power minus 1 divided by T. So if T is not given, we have to make an assumption of T is equivalent to 0.1 second. Okay. The next one, how to design an IAR filter using impulse invariance method. So let me see what are all the steps behind over on it. The step 1, for the given specification, find H of S, nothing but a transfer function of an analog filter. And then step 2 to be we have to select the sampling rate of the digital filter. Okay. Step 3, we have to express the analog transfer function. That is, we have to given as an H of S is equivalent to summation n is equivalent to k, summation k is equivalent to 1 to n Ck divided by S minus Pk. That is, we have to compute the Z transform by means of an e power minus Pkt Z power minus 1. So for highest sampling rate, we'll be having of an T divided by. Okay. So for the analog transfer function, H of S is equivalent to 2 divided by S squared plus 3S plus 2. Determine H of Z using impulse invariant transformation if T is equivalent to 1 second and if T is equivalent to 0.1 second. So 2 different cases we are going to analyze over here. So what is the first step? The first step is to be H of S is given. It is given as an 2 by S squared plus 3S plus 2. So use your partial fraction. When you are using a partial fraction, it is given as 2 divided by S plus 1 into S plus 2. So you take over that A by S plus 1 plus B by S plus 2. So find the value of A and B. Okay. So A is equivalent to 2 and B is equivalent to 2. So we'll be replacing that is by A by S plus Pi is equivalent to A by 1 minus E power minus PIT Z power minus 1, because your poles here to be poles 1 is equivalent to 1 and the poles 2 is equivalent to 2 over here. So we'll be replacing by 2 by 1 minus E power minus T Z power minus 1 minus 2 divided by 1 minus E power minus 2T Z power minus 1. So we have to analyze for 2 different cases when T is equivalent to 1 second and when T is equivalent to 0.1 second. Okay. So we'll be doing over here. So 2 divided by, so substitute the value of E power value, E power minus 1. We'll be getting minus 0.1353 and E power minus 2, 0.1353. So do the 1367 So do the multiplication over here. So we'll be doing the cross multiplication. So 2 into 1 minus 0.1353 minus 2 into 1 minus 0.3679. Then 2 minus of this value, then minus 2, minus 2 of in this value, 2 and minus 2 will be getting cancelled. So we'll be getting of expression 0.4652 z power minus 1. Similarly, multiply with this factor 1 into 1, 1 minus 0.1353 minus 0.367 minus into minus will be plus, multiplying 0.0498. When you are simplifying, you will be getting that 1 minus 0.5032 plus 0.0498. Okay, so take the highest factor to be out, z power minus 2. So z squared minus 0.5032 z plus 0.0498. So this will be getting cancelled. So we'll be getting the final expression h of z equivalents to 0.4652 z divided by z squared minus 0.5032 z plus 0.0498. Okay, so this is the value for the case of an t is equivalents to 1 second. Similarly, when the case of an t is equivalents to 0.1 second, so you replace t is equivalents to 0.1. So 0.1 is nothing but an e power minus 0.1, e power minus 0.2 into 2 over here. So we'll be getting the values 0.9048, 0.8187. Again, do the cross multiplication and then multiply this factor. Simplify a numerator expression and denominator expression. Then take down the highest factor to be out over there. Then the final expression 0.1722 z divided by z squared minus 1.7235 z plus 0.7408. So this is the way to compute Butterworth digital filter using of an impulse invariant method. Thank you.